The smallest engineer of this arc measures 5 micrometers across. It drifts in the surface of the sunlit ocean, armored in calcite. Over 40 million years, its ancestors built the cliffs you are looking at. The organism is a coccolithophore, a spherical single-celled phytoplankton of the haptophyte lineage. Biologists have described about 200 species. The most abundant one in the modern ocean carries the binomial Emiliania huxleyi, pronounced Emiliania huxleyi, recently reclassified as Gephyrocapsa huxleyi. The cells measure 5 micrometers across. Each secretes a covering of interlocking calcite plates called coccoliths, each 2 to 25 micrometers wide. The plates reflect light, and a coccolithophore bloom turns the ocean a pale milky turquoise that satellites photograph easily from orbit. A single bloom event can cover more than 100,000 square kilometers. When the cell dies, the coccoliths sink. They settle on the sea floor as part of the pale calcareous ooze that covers roughly 35% of the deep ocean floor. The scale of what coccolithophores do is difficult to hold in mind at first. Each one photosynthesizes, producing sugar and oxygen from dissolved carbon dioxide. Each one also builds its coccoliths from calcium and bicarbonate ions, using energy from that same photosynthesis. The two processes pull carbon in different directions. Photosynthesis removes CO2 from the surface water, calcification releases it. The net effect on the carbon cycle depends on where the cell eventually sinks. If it sinks far enough and fast enough, the sequestered carbon stays on the seafloor for tens of millions of years. If it dissolves on the way down, the carbon returns. Across the global ocean, coccolithophores are responsible for between 1 and 10% of primary carbon fixation at the sea surface. They are the dominant pelagic producers of calcite, meaning, in plain terms, that most of the calcium-carbonate on the ocean floor that wasn't built by a coral reef or a mollusk shell came from a coccolithophore. In the late Cretaceous, between about 166 million years ago, the shallow epicontinental sea that covered much of what is now Europe was full of them. The seabed, year after year, received a near-continuous rain of coccoliths. The accumulation rate was slow, about 0.5 millimeter per year, or roughly 180 coccoliths piled one on top of another. Over the span of the late Cretaceous, those millimeters added up to sediments 500 meters thick. Lithification turned that sediment into the chalk group. The formation today runs from Ireland through southern England, under the English Channel, and on into northern France. The White Cliffs of Dover stand as the most visible edge of this formation. The cliff face reaches a height of about 110 meters, 350 feet. The chalk itself consists almost entirely of coccoliths. On the 26th of August, 1868, Thomas Henry Huxley stood in front of the working men of Norwich during a meeting of the British Association for the Advancement of Science. He titled his lecture on a piece of chalk. Holding up a piece of English chalk, Huxley explained, using a single-hand lens and some patience, that the chalk consisted of the microscopic skeletal plates of animals long dead. From one piece of rock, he argued, one could reconstruct much of Earth's geological history. Macmillan's magazine printed the lecture later that year. It stands as one of the clearest pieces of science writing in the English language. About a century after the lecture, the most abundant living coccolithophore received a formal name. The binomial is Emiliania huxleyi. The name honors Cesare Emiliani, the Italian paleoceanographer who worked on its sediments, and Thomas Huxley, who had held up the chalk and explained what it was. The species is not just geological history. In this century, the organism has become a subject of active climate research. In 2008, Maria Iglesias-Rodriguez and colleagues published a paper in Science demonstrating that Emiliania huxleyi, contrary to expectation, increases its rate of calcification when grown under elevated carbon dioxide. The ocean acidification story turned out to be more complicated than a simple decline. The coccolithophore's ultimate response to a warmer, higher carbon ocean remains under investigation. For now, the bloom images keep arriving. NASA's MODIS and Landsat satellites routinely photograph them. Pale milky swirls hundreds of kilometers across, visible from space because a trillion small shells are scattering light at the surface. 4 episodes. 4 animals that seemed individually small: a beaver, a coral polyp, an earthworm, a single-celled alga. Each one multiplied across a continent or an ocean and counted over geological time, became an engineer of the landscape it lived on. The naturalist returns in the next arc, from the ecosystem scale back to the individual. Ecosystem engineers.